Hey everyone, in this video we're going to learn how to write a quadratic function in Vertex form. To start, we're going to graph f of x equals x squared plus 2x minus 3. So when given a quadratic function in standard form, the easiest point to identify is the y-intercept. So that's going to be 0, negative 3. So this is great review of graphing a quadratic. Next, we can find the axis of symmetry, which is x equals negative b over 2a. So in this case, that's negative 2 over 2 times 1. So that's x equals negative 1. So the vertex is negative 1, comma. We need to find that y value. So we'll plug negative 1 into the function. So negative 1 squared plus 2 times negative 1 minus 3. So 1 minus 2 minus 3 is negative 4. We also need the x-intercepts, and those occur when y equals 0. So we'll set the quadratic equal to 0. We can factor x plus 3 times x minus 1 equals 0. So either x equals negative 3 or x equals 1. So the x-intercepts are negative 3, 0, or 1, 0. Okay, so plotting all of our points, 0, negative 3, negative 1, negative 4. By symmetry then, negative 2, negative 3 is also on the graph. Then the x-intercepts at negative 3, 0, and 1, 0. So we can connect our points to create our parabolic curve. So there's the graph of f of x. So they ask us to state the transformation performed to y equals x squared to produce the graph above. Well, if we recall, y equals x squared has a point at 0, 0, negative 1, 1, 1, 1, 2, 4, negative 2, 4. So we're comparing those points to the points on the graph of f of x. And looking, there does not seem to be a scale factor, just a translation. And the translation is left 1 and down 4. Okay, so state the transformation. So it's left 1, down 4. If we write it in our shorthand notation, that's a translation of negative 1, negative 4. So let's take the parent function, y equals x squared, and let's apply that translation to the function. So we'd wind up with y plus 4 equals x plus 1 quantity squared. Remember, the equation is always opposite what the translation is. So if we're adding negative 1 to x, then we're adding positive 1 inside the parent function. And same thing for y. If we put this in y equals form, we'd have y equals x plus 1 squared minus 4. So we did this quite a few times in our transformations unit, but now that we learned completing the square, this expression, x plus 1 quantity squared minus 4, looks really familiar. It looks exactly like what we would get if we complete the square. And on top of that, what was the vertex? The vertex was negative 1, negative 4. Look what our translation was, negative 1, negative 4. So there seems to be a connection now between completing the square and vertex that's going to give us another way to write a quadratic function. So we can use the technique of completing the square to write a quadratic function in vertex form. So that's our new form. This will allow us to identify the transformation of y equals x squared that will produce the graph of the given quadratic. So essentially, by completing the square, we're setting it up to be written as a transformation. And we've done transformations, so that will make it easier for us to graph. So rewrite f of x equals x squared plus 2x minus 3 in vertex form. So completing a square, we're going to put a set of parentheses around x squared plus 2x. So we have f of x equals x squared plus 2x plus something minus 3. So to figure out what value creates a perfect square trinomial, we're going to take half of 2 and square it. so 1 squared is 1. The coefficient here is 1, so 1 times 1 is still 1. So then we'll subtract 1 to keep the expression the same. But what we've done is allowed ourselves to create a perfect square trinomial that can be factored. So x squared plus 2x plus 1 can be written as x plus 1 quantity squared minus 3 minus 4. So then, or I should say minus 3 minus 1 is minus 4. So we have f of x equals x plus 1 quantity squared minus 4. So this is vertex form. Notice we're able to rewrite this so we can identify the translation. And then to find the vertex, just apply that translation to the vertex of y equals x squared, which is 0, 0. So how can we determine the vertex of the parabola? So as we just said, identify the transformation. So f of x plus 4 equals x plus 1 squared. So the translation there is negative 1, negative 4. So we're going to take the vertex. So vertex of y equals x squared. We're going to apply the translation. So we would get negative 1, negative 4. And this is the vertex of f of x. Okay, so by rewriting a quadratic in vertex form, we can identify the vertex a little bit easier than using the axis of symmetry and then plugging it back in. And then graphing, we can graph it with transformations as opposed to the way we graphed it in that first example, which was to find all of the critical points and then plot them on the graph. So rewrite the following quadratic functions in vertex form by completing the square, identify the vertex, and state whether it is a maximum or minimum. So our first function, f of x equals x squared minus 10x plus 7. So we'll put a set of parentheses around x squared minus 10x. So f of x equals x squared minus 10x plus something plus 7. Okay, so the value that creates a perfect square trinomial, we're going to take half of negative 10. Well, let's clean that up. Looks like a messy expression down there. So half of negative 10. And we're going to square it. So that's negative 5 squared, which is 25. So we'll subtract 25 from our expression as well. So that gives us f of x equals x minus 5 quantity squared. And then 7 minus 25 is minus 18. Okay, let's just try to identify the vertex without rewriting it. Let's see how that would work. So our vertex. So x minus 5 means we're moving 5 to the right. So x coordinate would be 5. And then if we add this over, it would be f of x plus 18. So that means we're moving down 18. So minus 18 would be the y. All right, so if we took 0, 0, the vertex of the parent function, and we applied this translation, we'd be moving right 5, down 18, to get a vertex of 5, negative 18. Now, whether that is a max or min, we go back to the original function, and we look at the coefficient of x squared, the a value. In this case, a is positive. The parabola would open up, which means our vertex is a minimum. As a reminder, that's because a is positive. Greater than 0, not 1. Okay, f of x equals negative x squared minus 8x minus 1. So again, we'll start by putting a set of parentheses around negative x squared minus 8x. So we have f of x equals. Now in this case, we have that negative coefficient that we have to factor out. So negative 1, x squared plus 8x plus something minus 1. So the value that creates a perfect square trinomial, we're going to take half of 8 and square it. So 4 squared is 16. Now when we think about what we have to adjust here, Remember, we have to think about distributing that -1 out first, so it would really be -16. So we're subtracting -16 to keep things balanced. So that means f of x equals -1 times x plus 4 squared after we factor the perfect square trinomial. And then -1 plus 16 is plus 15. So our vertex, okay, so we're moving x to the left 4, so -4. And then we'd have f of x minus 15, so we're moving y up 15. So -4, 15 would be the coordinates of the vertex. Notice that coefficient does not affect the translation, so it does not affect the coordinates of the vertex. And then, go back to the original, the coefficient of x squared is negative now. So that means the parabola opens down, so the vertex is a maximum. Again, that's because a is negative. Right? And just something I mentioned earlier, right? The scaling doesn't affect the vertex. Remember, we're transforming the vertex of the parent function, which is 0, 0. And a scaling is a multiplication. If we multiply 0, 0 by anything, we'll still be 0, 0. And then we would translate it. So that's why when we're stating the coordinates of the vertex, we only focus on the translation part. Same directions, new function, f of x equals -2x squared plus 10x minus 19. So we put a set of parentheses around -2x squared plus 10x. So we have to factor out the -2. That leaves us with x squared minus 5x plus something minus 19. Okay, so the value that's going to complete the square, that's going to be half of -5 squared. So we'll leave as a fraction. When we square it, we get 25 over 4. But again, we have to think about distributing that leading coefficient. So to keep things balanced, we have to subtract by -25 over 2. Right, -2 times 25 over 4 would be -25 over 2. So we have f of x equals -2. Now factoring the perfect square trinomials with a fraction, a little bit challenging. So we use the fact that we take half of the -5 in our factors, so -5 over 2, so x minus 5 over 2 squared. And then let's see here. So this would become -38 over 2 plus 25 over 2. So that's going to be minus 13 over 2. Okay, so our vertex, so we'd be moving 5 over 2 to the right. So 5 over 2 is the x value. And then if we move this over, f of x plus 13 over 2, so we're moving down 13 over 2, so minus 13 over 2. And if we look, that leading coefficient is negative, so that means our vertex is a maximum. Again, that's because a is less than 0. Next up, we have f of x equals 1/2 x squared minus 4x plus 11. So we start by putting a set of parentheses around the 1/2 x squared minus 4x. So we need to factor out the 1/2. So that's x squared minus 8x plus something plus 11. Again, if we're factoring out a half, think if we distributed the half back in, 1/2 times -8 would be -4. Right? So if you don't see the factoring, taking out a half from 4 as being 8, go the other way. 1/2 times -8 is -4. So now finding the value that creates a perfect square trinomial, so that's -8 over 2 squared. So -4 squared is 16. Remember, I have to multiply that leading coefficient though before I figure out what to subtract by. So that's 8, so I'm really subtracting by 8 to keep everything in balance. And if you're ever not sure, simplify it. Do the actual simplification and see that you get 1/2 x squared minus 4x plus 11. So we have f of x equals 1/2 times x minus 4 squared and then plus 3. So the vertex here, well, x minus 4, 4 to the right, so that's positive 4. And then fx minus 3, so we're going up 3, so 4, 3 is the vertex. That leading coefficient is 1/2, so that's positive. So that means our vertex is a minimum. Right? A was greater than 0. Now, rewriting a function in vertex form can also be helpful in projectile motion questions. So going back to a projectile motion word problem, a model rocket is launched from the ground and its height in feet is modeled by the equation below with t measured in seconds. Determine the maximum height of the rocket by rewriting the equation in vertex form. So essentially, they're looking for the vertex here, right, maximum height. So by using completing the square, we can rewrite this in vertex form. So we'll start the same way. We'll put a set of parentheses around negative 16t squared plus 96t. So h of t, we need to factor out the negative 16. So that's t squared minus 6t plus something. So half of negative 6 squared. So that's negative 3 squared is 9. So then we're going to subtract. Well, we have to distribute out the negative 16. So negative 16 times 9 is negative 144. So we're subtracting negative 144 to keep everything in balance. So then we have h of t equals negative 16 t minus 3 squared plus 144. So our vertex here is going to be t minus 3, so that's 3 to the right, so 3. And then h of t minus 144, right, if we move this over, we'd be going up to 144. Okay, so the question asked us to determine the maximum height of the rocket. So they're asking for the y value of the vertex. So 144 feet. If they asked when, well, that's the t value in this case, which is 3, right? It happens when we're at 3 seconds. Okay, so this is how we can use vertex form to answer some of those projectile motion questions as well. So now practice rewriting functions, quadratic functions in particular, in vertex form, which is really just practice with completing the square. And then we're going to use this to help us graph in the next video. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.